right, so another way for us to calculate delta H is with a calorimeter. We have used calorimeters in the lab already, but now we're kind of going to use some math with it. So a calorimetry is the measurement of heat transfer. A calorimeter is the device we use to determine that amount of heat transfer. Sorry, dog. Hello. She's kind of gross, sorry. Other dog is staring. Other dog. Okay. So, the calorimeter that we used in the lab was a foam coffee cup. Heat flow cannot be measured directly, so we measure the temperature before and after the reaction, and we use that data and we do some calculations to figure out the heat transfer. This is kind of what it looks like. The amount of heat absorbed or released during a physical or chemical change can be measured, usually by the change in temperature, which we call calorimetry, and in that quantity of water, this is the calorimeter basically. This is the kind that we use. We put a thermometer in. We've got water in there. We've got a lid, and we make our reaction. Apparently they have a stirrer right here to figure out the heat transfer. Oh. All right. So moving on. In coffee cup calorimetry, which is what we do, we're measuring the heat lost or gained using the temperature change. We use this equation where we have delta Q, or just Q, the heat lost or gained by the solution in the reaction, equals the mass, which is in grams, C, which is the specific heat, which we will use this number very frequently, especially if our concentrations are low. And then delta T is your T final minus that T initial. And that can be in degrees Celsius or Kelvin, it doesn't matter, it's the same number. So the reactants and products are in the system. They are the system, sorry. So your reaction is the system. The water which they are dissolved in is the surrounding. So the water, it changes its temperature. That is the surroundings. The heat lost or gained by the solution is equal to the heat lost or gained by the reaction. So if the heat gained by the water is 20, then the heat lost by the reactions of the reactant products is 20, or negative 20. So if you calculated delta Q of the solution to be 568 joules, the solution gained heat because it's positive. This means that the reaction was exothermic. The heat gained by the solution is equal to the heat lost by the reaction, which would be the same number except negative. And that's going to be your reactants and products. Those are the system. That is the reaction. So let's jump right into a practice problem. Example 1, a 97-gram iron bar was heated to 143 degrees Celsius. So this gram iron bar was originally that hot. And it was placed in the coffee cup calorimeter, which is dumb at that temperature, containing 350 grams of water, and the water is at 25 degrees Celsius. The maximum temperature of the water was measured to be 28.40 degrees Celsius. It asks a variety of questions. How much heat was gained by the water? How much heat was lost by the iron bar? And what is the specific heat of the iron? So if I start right here, how much heat was gained by the water? So I'm just going to do Q equals MC delta T. Q is what we're looking for. Mass of my water, I was given 350 grams. C for water is 4.184 grams per, joules per gram degree Celsius, times by our delta T, which I'm going to do for the water is 28.4 minus 25. I do all that and my Q comes out to, that's my dog. Q comes out to 79 joules is our unit there. How much heat was lost by the iron bar? It's just the negative of that number. Q equals negative 4,979 joules. Very simple. Then from there, I can move on to what is the specific heat of the iron. Well, if I know the Q of the iron, then I can figure out that C. So Q is negative 4,978.96 technically, equals M for the iron was 97 grams. C is what we're looking for, and delta T for the iron was 28.4, which is our T final, minus our T initial, which is actually larger at 143. I do the math, and my C comes out to 0.4479. And that's going to be joules per gram degree Celsius. Example number 2. When 20 milliliters of 1 molar NaCl at 22 degrees Celsius is mixed with 20 milliliters of 1 molar AgNO3 at 22 degrees Celsius in a calorimeter, a white precipitate forms, and the temperature of the mixture reaches 29.6 degrees Celsius. Assume that the specific heat capacity of the mixture is 4.184 joules per gram Kelvin. Its density is 1 gram per milliliter, and the volumes are additive. It says, first, write the net ionic equation for this reaction. So the net ionic equation is very, very simple. It's just, so NaCl plus AgNO3. They all have plus and minus 1 charges, so it's really easy to combine those. NaNO3 plus AgCl. The AgCl is my solid, so my net ionic equation, sorry, my dogs are now playing, like right behind me. Dogs, what are you doing? What are you doing? Oh, okay. All right. The net ionic equation for that comes out to Ag plus Cl minus yields AgCl. Solid. Very simple. It says calculate delta Q of the solution. So delta Q of the solution, trying to look for it. We've got 20 grams, so we get that from the density and the milliliters. So if we're given 20 milliliters of one of them, it might, sorry. Hold on. Okay, so I had written 20 grams as my mass before, but it's actually 40 grams because we have the 20 milliliters of the NaCl plus the 20 milliliters of the silver nitrate, which gives us 40 milliliters. We're kind of assuming that the density is 1. It says the density is 1, which gives us 40 grams total. So Q equals 40 grams times our C, which they said was 4.184, times our delta T, which is 29.6 minus 22. The dogs are super playing now. Okay, we're just going to ignore them. Q for the solution is negative 1,272 joules. Positive. For the reaction, the Q is negative 1,272 joules. It's just the negative of that. Now jumping down, calculate the moles of Ag or Cl. If our molarity is 1, so we have 1 mole per liter, and we were also told that there was 0.02 liters of Ag, for instance, then we have 0.02 moles of Ag. And looking at our net ionic equation, there's 1 mole of each thing. So if there's one mole ratially of that, then there's 0.02 moles of pretty much everything. So I have 0.02 moles, and I got my joules earlier. I converted the joules to kilojoules, so it's just 1.272 kilojoules per 0.02 moles. And I get a delta H of 63.6 kilojoules per mole. All right, so the delta Q of the reaction is the heat lost or gained in the experiment that took place in the calorimeter, whereas the delta H is the heat lost or gained in the balanced chemical equation. So this is the heat lost in the experiment, whereas this is the heat lost in the equation. Okay,